Let's continue in 6.5 on pumping liquids from a container, the work done by pumping liquids from a container. So we just did 6.5. The previous video is on a constant force. We looked at that basic definition you would see in a simple basic physics class. And then we looked at the variable force, the calculus-based variable force concept. And you get this integral. So the integral is a distance integral. You're integrating distances, little pieces, and adding them up. And then this, of course, is a force. So then the force times the distance is the work, and you add it all up. So we're going to do the same sort of thing, but with pumping liquids. It's a pretty typical type of problem, and this is what I'll focus on in this section. So let's write this down. A right circular conical tank of altitude 20 feet and base radius of 5 feet is full of water, weighing 62.5 pounds per cubic foot. Find the work done pumping all the water over the top of the tank. Okay, so I read it once all the way through. Now I'll go back through and read it again. So conical tank means a cone. Altitude 20 feet. Okay, so it's the height of the whole thing. Base radius is, at the base, and that's the top, but we still call it a base radius of 5 feet. Of course, to hold water, you have to have a cone, like an ice cream cone, in this orientation. Okay, so it's full of water, so there's my liquid water, like that. And this gives you, it always gives you the weight in the different units just to describe the weight of water. So if you know the volume, then you know the force acting on the water by gravity. Basically, that's your pounds, because your force is a pound. So 62.5 pounds per cubic foot is what we'll use. So the force of due to water is going to be your volume times the 62.5 pounds per cubic foot. So when we look at our work, we're going to take that 62.5 and it'll just factor out. Then you multiply times the volume and the distance. You're basically, for water, it's gravity, so you're lifting it like that, lifting it up and out of something. So it's the distance lifted is what you're going to calculate. So let's look at what you're actually lifting out. You want to focus on basically these slabs of water. So take one little slab of water like that, okay, and the radius change. The whole thing changes as you go up. So that slab of water compared to the one down here is different, right? It's a different volume because it's a different type of figure, and then you're going to lift it a different height. So that changes as you go up. So let's look at a couple different things. When you look at the increment of the slabs that you're lifting up, the slab of water, is it delta x or delta y? Is your thickness delta x or delta y? And we can see here it's delta y. Okay. Now, you can drop down where you are in your x-axis like this and consider that your x, and then there's a y value up here. We don't know what those are, and those change. But we do know basically what the picture would look like. So let me do this. So we have, let's look at the volume. Let's just do one thing at a time. So forget about the distance and stuff. Let's just look at the volume of the little slab. So what is it? What type of figure is it? So it's the volume of the little cylinder, basically, right? So the volume of the cylinder is pi r squared h. That's the volume of, we know that is the volume of always a cylinder. You get the area of the circle times the height. So if we convert that to things we know, what is the radius of these little circles? Okay, and so it would be wherever you are on the x-axis. So we would say that this is equal to pi, and then it's x squared. And then what's the height of those little things, these little pieces? Well, that's your delta y. Okay, so what is the issue or problem right now that we have if we write it in terms of x squared and delta y? Well, the variables are wrong, right? So if you have a delta y, then we need to change your x in terms of y. So we can do that because we know that this is the side of, that's the relationship, that line. As x goes out, y changes accordingly as you go out, right? Like that. And so we can figure that out. So what we can do is we can draw in a rectangle here. So basically, I'm taking this, and then I can figure out the slope of that line. Might be obvious to you. It doesn't really matter. I'll go ahead and do it here. So let's calculate that just by the points we have. It doesn't have to be to scale or anything. I'm just showing you how I can look at it. So you have this triangle. That's the cross section of that cone. And we know that if this is 5, then the height here is 20. So your delta y over delta x, probably a poor choice of values for our deal there. Your slope of that is the change in y over change in x. So that's going to be 20 over 5 or 4. So this line here is going to be what? That line is, there it is y equals, let's do it down here, y equals 4x. Or you can solve for x, because that's what we're going to need. You have x is equal to 1/4 y. Okay, so that's how we can get the relationship of the x and y. So now we can substitute back into here for x. And so that equals pi, and then times 1/4 y squared delta y. So that's the volume we have. Then we know the force is going to be the 60, all you got to put in is the 62.5. So 62.5 times the volume is going to be the 62.5 times pi times the 1/4 quantity, 1/4 y quantity squared delta y. All right, so then we have just what's the work function going to be? I'm just moving this for space. So then work is going to equal your force, which is above, times your distance. So what's the distance you are lifting this slab out? So wherever you're at, say it's here at y, then what's this distance right here? Well, it isn't y, because if you're down here, that would be the y distance. It would be the total distance up and out. It is just to the top. It's just to the top of it. It's not, a different question actually is 3 feet above or something. We're not doing that, okay? We're doing right to the top and out. So the distance would be 20 minus y. So this distance here to here is 20 minus y. So let me write that down. So distance lifted out to the edge, not above it, that's a different question, is 20 minus y. So that's your d. And it's variable, right? It changes as you go up or down, of course. So your delta W, meaning each increment as you lift it out, if you focus on just lifting out one piece up and out and then adding them up, then you'll be good. So your delta W is F, change back, F times D, which is 20 minus Y times your 62.5 times pi times 1 over 16, I'm just going multiplying it out, y squared delta y. So how many times, or from where to where, from what value to what value are we lifting these pieces? We're integrating from the bottom all the way to 20, so it's each piece. So that's 1, then 2, etc., all the way to 20. So our work equals the integral, this is your summation part, from 0 to 20, 20 minus y, 62.5 times pi, 1/16 y squared dy. Once you have that, I mean, the rest is just simplifying that integral, pretty straightforward stuff. So I would factor out everything that you can. So 62.5 pi over 16 times the integral, times the integral from 0 to 20. So what you're integrating, you always have to focus on, like, if you were to go above the tank, this is kind of getting ahead of us, but if you go above the tank, then it would be like, maybe, like 10 feet above the tank, then that distance would be like 30 minus y. But you're only integrating or adding up the pieces from 0 to from 0 to 20. So it's this one, then the next one, the next one from 0 to 20. Okay, so okay, then multiply it all out, and I'm taking some liberties here to kind of go ahead. So work this out on your own. It should be pretty straightforward once you get this form. Just polynomials, all in terms of y. Okay, so I worked it out. You can check it. And I get 62.5 16ths pi times 40,000 over 3. And then you can get an approximation for this one because it's, you're just doing, it's an application. 163,625 foot-pounds. So if you pick, I mean, that seems like a lot, right? It should be, right? I mean, you have a 20-foot high tank that's 5 feet wide. If you're going to pump that over and out, think about how the value it should be. Okay. We will do another one. Same type of question. And yeah, we'll probably then we'll reserve the rest for problem sessions and stuff.